Okay, so what we're going to do now, we're going to look at the last geometric shape, that is a sphere, for this alternative method of doing conduction analysis. So we're going to look at a sphere. And we are going to assume that it is radial conduction only. And the other assumption, steady state. 1D, no heat generation. And the last one is K is equal to constant, so it's not a function of temperature. So those were all the requirements that we had for this alternative method. I'll begin by drawing out a sphere, and then we'll work through using Fourier's law. Okay, not a great sphere, but it is a sphere nonetheless. So what we have some hollow sphere, and we're going to say we have internal radius Ri, we have outer radius R naught, and we're interested in what's going on at some arbitrary radius R, and we're going to then try to solve for T at R. And temperatures, those are the boundary conditions we're going to have. Let's say that we know Ti and we know T outer. All right, so that's the information we have. The area of a sphere, you better know the area of a sphere. The volume of a sphere is 4/3 pi r cubed, and the area would be the derivative of that with respect to r. So area is 4 pi r squared. All right, that's the area of a sphere. You have no idea how many times during exams I have students ask me, what's the area of a sphere and what is the volume of a sphere? Those are things that you should have memorized. That and the quadratic equation. Remember, memorize those things. Okay, here we go. Fourier's law. We have Fourier's law. We're going to rearrange that. We put in the area of the sphere. And we're going to integrate this to our arbitrary R location. Okay, so we get that equation there. Now what we want to do is we want to integrate that. And looking at this equation here, remember this is the thing that we're after. We want to have a way to determine the temperature distribution within our hollow sphere. So we rearrange this and we can come up with the following expression. And we get this relationship. Now, like before, we have not finally solved everything, so we still have that heat flux in there. How are we going to get that? Well, we have our boundary conditions. Coming back here, we've used this boundary condition, we haven't used that one. So let's apply the boundary condition. Okay, there we go. So that gives us the heat loss for this spherical object, where we know the inner and outer temperature as well. It gives us the temperature distribution. So those are three different things that we can do. We've looked at spherical, cylindrical, and we looked at one-dimensional. That was for the conical section. As long as you know the area as a function of position, and you can assume it to be 1D, steady, no internal generation, and the thermal conductivity being a constant as a function, not a function of temperature. If you have all of those, you can come up with these equations. So we've done a lot with this, but what we're going to do in the next lecture, engineers are lazy. Not quite. We're not lazy, we're efficient. So what we're going to do, we're going to package all of this stuff together and come up with a more compact way of being able to apply these ideas and apply them to calculations in a fairly quick manner. And so that's what we'll be looking at in the next lecture as we continue on using the alternative method